Today we're going to continue our discussion of transactional memory. We'll talk about software and hardware implementations. Just to kind of remind you of where we left off at the end of last lecture. We talked about, during the lecture we talked about all the transactional memory properties that we wanted to preserve. And we talked about the advantages, and then we talked about the different kinds of aspects of the transactional memory design that you needed to consider. One was sort of what data versioning policy you use to keep track of the old transactional data that had been committed and the new transactional data that is being created as the transactions execute, and then how we actually detected conflicts between transactions. And we said there were two data versioning policies, eager and lazy. And then we said that there were two conflict detection policies, pessimistic, where you detect the conflict as the memory references are made, and then optimistic, which assumes that there will be no conflicts, and you detect the conflicts when the transaction, when any transaction commits. All right? And so we did some examples, and we saw that in a certain case of case 4 for the pessimistic conflict detection policy, that sometimes we had a situation where we had live lock and we needed to detect that, and the transactional memory system would have to recover from live lock to make sure that the application could make forward progress. And then we also did the optimistic case, and we saw in the case where you had live lock, in the pessimistic case you didn't have live lock here, and the reason is, of course, is that the committing transaction always wins, right? And the committing transaction, remember, the check was you compare the write state of the committing transaction with the read state of all the outstanding transactions that are still in execution. And if there's a conflict, then those transactions have to abort, and the committing transaction gets to commit. Okay. So any questions on what we've discussed so far as the way transactional memory is supposed to work and the properties that needed to be preserved? All right, so let's discuss an explicit implementation or a couple explicit implementations. As you can imagine, given that you've got a space of policies that you can implement, there's a wide range of different implementations that pick different points in the design space of the policies that you select, right? So you can have lazy optimistic, you can have eager optimistic, eager pessimistic. As we've already discussed, eager optimistic doesn't work out too well, right? Because at the point at which you detect that there is a conflict, you may have already kind of modified the memory in ways that are difficult to recover from. So those are the software systems. The software system that we're going to look at is in fact a kind of hybrid that is eager optimistic for reads but pessimistic for writes. And we'll see how you can have both at the same time by treating reads and writes slightly differently. And then, of course, we'll also look at some hardware TM systems. First of all, we're going to motivate why you want hardware. And, of course, you always want hardware if you want to improve performance, right? And so, there are performance overheads that we'll see from the software systems that can be mitigated by using hardware. And, of course, you can have some sort of hybrid where you kind of mix hardware and software, and you try and attack the components of the software systems that are really going to provide the most overhead, and try and reduce those overheads by judicious use of hardware. Okay, so let's start by looking at software transactional memory implementation. And this is sort of, a canonical way of implementing a transactional system in software, but you could, it's applied in this situation to transactional memory, but you could imagine implementing something like this for other cases where you wanted to keep data consistent in some manner. All right, so given this atomic region, right, you've got reads and writes that are shown in the code here, in the statements of the code, and somehow you need to indicate to the transactional memory system, what actions are being taken place inside the program. And that is done by the use of what we call software barriers. And software barriers are basically calls into the transactional memory system to indicate to the system, what bookkeeping has to be taken, right? So the idea is that you've got to rewrite the code that the programmer gives you and add these extra calls into the transactional memory system. So for every write, you need to, put in a TM write, and for every read, you need to make that into a TM read. Okay, so these are called software barriers, not to be confused with barriers for synchronization, right? This is just basically a call into the transactional memory system specified by these TM read and TM write functions. So you need this bookkeeping, of course, to keep track of what's happening with the state of the transactional memory system. As we'll see, a lot of these TM calls are redundant, and you can kind of optimize them away, and we'll see an example of that, in just a moment. All right, so we've essentially now have to translate this code on the left, which the programmer wrote, into something that interacts with the transactional memory system. And of course, if you have code that is both executed inside transactions and outside transactions, then you need two copies. One that doesn't have the instrumentation on the left, and one that does on the right. And if you've got some sort of virtual memory system, such as if you're running in Java or in C#, then maybe you can do some of this, what's called function cloning automatically, where you clone the function and you add the appropriate software barriers to interact with the transactional memory system. All right, so now the question is what data structures do you need to keep track of the transactional memory state and make sure that everything operates correctly, right? So you need some way of sort of mapping the data that is being manipulated by the application into the data structures that need to be used to track the transactional memory state. And so this is called a transactional descriptor. And this can be two components. There's a transaction descriptor, which is per thread, right? So this is information about undo logs, write buffers, conflict detection, and the sort. Read. So you need the read set, and the write set is also part of the transaction descriptor. And this is per thread or per transaction. You need a transaction descriptor, and then you need a transaction record per data element, and this could be associated with objects or with a finer granularity of data within the objects, right? And so essentially here with the transaction record, you're going to essentially keep the metadata that tells you how the data is being accessed, right? And so if you make an analog to our discussion of cache coherence, right, where we said that you needed the cache state to tell you whether the data was shared, by multiple CPUs, or in this case, multiple transactions, or whether it was exclusive to one transaction, right? So there's a direct analog between the way that we handle transactions and the way that we discussed, doing cache coherency. Okay, so then the question that is, how do you actually map the data that is being used into the program, but by the program, to the data to the transaction record, and so you can do this in two ways. You can do it per object, where each object has a transaction record, And so this is shown by the kind of the top. You can either use some sort of table associated with the object, or you have some hash into a global data table. Or you could do it, per individual data element, right? And of course, if in C or C++, where you might have to do this based on address. And so the question is, of course, this is a finer granularity of information about the data than doing it per object, right? So there is some trade-off to be had. And as you're already, thinking about this, because you're making the analogy to cache coherence, you're thinking, so what is the trade-off that we're going to see between doing things at the object level or doing things at a finer granularity at the individual field or individual 32-bit or 64-bit data element level? Yeah.
I guess when you have like something that's at an object level, you assume all the properties are like handled together, even though they could actually be independent. Like X and Y can be independent, so you prefer finer grain.
So what is going to be the impact of doing that?
If it's not independent, then the transactions like we saw previously, the wing transaction memory works. It will have unnecessary like aborts and restarts.
Exactly, right? You'll have more conflicts than really required, right? So this is exactly the trade-off. And so for object granularity, you're going to have lower overhead of actually keeping track of the data, and you might have some opportunities for optimization if you are doing repeated. You're previously using the same object, then you can amortize the overhead of managing the data record for that object. But the key thing that you do get with this coarser granularity are these false conflicts, as you pointed out, right? So here's the example then, right? So if you've got element or field granularity, then you can reduce the incidence of false conflicts and potentially improve concurrency. And if you look at the example on the right here, we access the field X and Y from object A in transaction 1, and we access the field Z in transaction 2. And if you're doing things on an object level, of course, these two transactions conflict. But if you're doing things at a field level of granularity, then there is no conflict, right? So that's the benefit. And of course, the downside of doing things at the element or field granularity is increased overhead, right? And then, of course, you can imagine doing things at cache line, because that matches what you might do in hardware, but then this doesn't have a direct analog with what you wrote as a programmer, so it might be difficult to understand what's going on. And if you're doing things in software, you can mix and match things, right? You might say, well, for objects, I'm going to do things. I'm going to do things at the object level, and then for arrays, I might think about doing things at the element level. And this turns out to be a pretty good trade-off. Okay, so with that in mind, so we have a way of thinking about data structures per transaction, the transaction descriptor, and then we have the data record for the individual data. So now let's talk about a specific STM algorithm. And the one that we're going to use, comes from Intel. It was developed quite a few years ago. It's called McCarty. And it is an eager versioning with optimistic reads, right? Which means we'll say explicitly how the reads are optimistic in just a moment. And then pessimistic writes, right? Which means you're going to take locks in order to do the writes. And so it's based on this idea of versioning or timestamping to determine what data is being shared by multiple transactions. And so the idea is that there's a global timestamp that is incremented when a transaction commits, right? So any transaction that commits in the system increments the global timestamp. And then there's a local timestamp which gets stamped on the transaction when it begins, okay? And so this will be used for determining whether conflicts happen on data. And then there's a transaction record associated with each of the transactions. And it's, with each of the transactions, so transaction record is associated with each of the data, I should say. And it's a 32-bit value with the most significant bit, the least significant bit is either 0, which means it's locked, and that means that this would be a transaction pointer. And then if the least significant bit is a 1, then this is essentially a version number. Okay, so by looking at the least significant bit of the transaction record, you can tell whether the particular object or the data element is so you can think of this as when you've got a 1, how should you think about the state of the data? Making analog to cache coherence. Yeah, it's shared, right? And when it's a 0, it's exclusive, right? And it's being written by this transaction, the one that says the pointer, right? So that's the way to think about things. So we're either in shared or exclusive mode, and the transaction record indicates that. All right, so now that we've got the notion of version tracking and transaction record, let's think about exactly what operations we need to perform in order to implement transactional memory in this software environment, right? So you've got, for every time that you want to do a read, you're going to call STM read. And this is optimistic in the sense that even though, as we'll see, you do try and validate the data that you are about to read, once you've done that, you're golden until some other transaction decides to commit. All right, so in this case, it's eager, so it's direct read from the memory location. You validate the data you're trying to read by checking to see that it's unlocked, right? So if it's locked, then what do you know about the data that you're trying to read? Yeah?
It could be invalid.
What do you know specifically that about the data that you're trying to read?
It could be stale because someone else could be writing.
Well, let's suppose that to make things a little more clear, let's assume that you're at a point in the program and you're doing this STM read, and you have a direct read from the memory, but you could potentially not read, right? You could do the check first. Let's assume you do the check first. Then what do you know? If the data is locked, what do you know?
It might be old. Like someone might be in the process of writing.
You know that there is a transaction that is writing that data, right? So, should you go ahead and read it? Probably not. You should probably, your contention manager might say, well, let's just wait. Let's just wait for that transaction to finish, and when it's done, then we'll read the data, right? So you can imagine at this point, if it's locked, that you just wait. If it's unlocked, that means that, some other, if it's unlocked and the data version is less than the local timestamp, what does that mean? Yeah.
It's in a shared state, so you can take it as exclusive now.
Okay, but what does it mean that the data version is less than the local timestamp? Yeah.
That means that something hasn't changed it before the transaction started.
Right. So while after the transaction started, some other transaction has modified it. Now, does it mean that this transaction has read the wrong thing? Not yet, because in fact the data has been updated. You know, it got the latest copy, right? But now it needs to make sure that all the rest of its data, you know, is actually good. And so it tries to validate the whole of its read set again. And we'll talk about exactly what that means. But it just wants to make sure that everything is up to date. Okay, so, you know, if we validated the read data, then we can insert it in the read set and return the value, right? So clearly there's more work to do with transactional memory than just reading the data, right? You need to keep track of the state of the transactional memory. Now, STM write is pessimistic in that you now have to check and grab a lock, right? So you check if it's unlocked and the data version is less than the local timestamp. If that check passes, then you acquire the lock, insert it in the write set, create your undo log entry, and write the data in place, because this is in fact eager, right? So you grab the lock, and that makes this policy for doing writes pessimistic. But it's optimistic for reads because you didn't actually check to see that there were any readers that had read this data here, right? So the readers can blithely go along. It might turn out that later, when this transaction tries to commit, that the conflict gets detected, but it doesn't get detected at the time that the write is happening. So in that sense, it's optimistic for reads. Okay, any questions? All right, so how do we do read set validation? Well, we get the global timestamp, and for each of the entries in the read set, we check that it's either, if it's locked or the data version is greater than the local timestamp, that we have to abort. What do we know has happened if it's locked? Yeah. Right, and you basically read the wrong thing. And it's also true if the data version is greater than the local timestamp. So that means that we've got bad data, and we need to abort this transaction and start again. Suppose every element in the reset checks, then we can kind of update the local timestamp for this transaction, because as if it started executing at this point in which you just got the local timestamp, as opposed to the original time that it got its local timestamp, which was earlier, because you've completely validated the read set at this point. Okay, yeah.
I think both of these checks, like lock by other or data version, I think like both of them can do the same thing, right?
No. What's the difference? Can someone enlighten us about what's the difference between the data being locked and the timestamp being updated? Yeah.
I'm pretty sure, so if it's locked, then another transaction is currently writing to that data.
Yeah.
Or if the data version is greater than what then it's already happened.
Exactly. That's the difference, right? One is the write's in progress. One is the write has already happened. Good. Okay, so STM commit, right? So now you need to increment the timestamp. You're going to do it by 2. Why do we do it by 2?
Preserves the error.
Yeah, because the least significant bit is actually, keeping track of whether it's locked or not, right? So we always have to increment it by 2 to make sure that we can use that least significant bit. Okay. Then we're going to take the pre-incremented, the old timestamp, and validate the read set. just to make sure that there aren't any recently committed transactions that would cause us to abort. And then for each item in the write set, we're going to release the lock and set the version number to the global timestamp. Okay? So that's it. So now let's look at an example, which is a slight modification of what I just told you, but it's close enough to make sense. So here what we're trying to do is we have two transactions, x1 and x2, and x1 is going to atomically copy object foo to object bar, right? And then x2 is going to read object bar, and it should read also atomically, right? And so it should read either 00 or 97, right? It shouldn't see any partial updates to the object. That clear? All right, so let's see how this works. So we start by executing the first read of foo, the x element of foo, right? And so this needs to go into the read set. So it goes into the read set as foo, and the timestamp is 3, right? So the idea is that there are no local or global timestamps here. Let's just assume that each of the objects has a timestamp, and the initial object timestamp for foo is 3, and for bar is 5, right? So we've got the read of foo in the read set with timestamp 3, and then we have a read of bar, and it gets timestamp 5, and so that goes into the read set of x2. Okay, and then we get a write to bar, right? And so what has to happen, right? We have to take the write lock, right? So we have a write lock, and that's indicated by the transaction pointer to x1. Okay, now we need to indicate that in the transaction descriptor by having updating the write set and the undo log, since this is a eager mode, right? So we have to have an undo log. So we put the old value of bar.x into the undo log, right? We continue executing, and we are going to read bar.y. So what should happen here?
Yeah.
Well, I think because like the granularity is of all bar, then it should say that's invalid.
So what should happen?
So it stalls, or either stalls. Or
Yeah. So maybe it's going to detect. It's going to see that bar is locked, right? So as it tries to do the validate for the read of bar, it's going to say, the object is locked, and so let's assume that we just wait, we stall. Okay? So x2 waits. Okay, so x1 continues. We have another read of foo, foo.y, and that gets put into the read set. And then we have another write of bar with that value, and that all gets put into the write set. Okay? All right, now we need to commit, right? And so what do we need to do on commit? Yeah. Is that the first thing we do?
No. I mean, like that you do that event. First, you want to actually do the commit and update the values.
So what do we do before that?
validate the read set.
Validate the read set, exactly. So first we want to make sure that the reads that we got are in fact valid. And so we check, and the timestamp for foo is still the same for both of the reads of foo. And so we say, read set validated, we're cool, and we can go ahead and commit. And the commit is going to increment the timestamp on bar by 2, so it goes from 5 to 7. Okay? Yeah.
So when we had the reads be two separate, like, is this two separate things in the read set?
Yeah.
But there's only one in the write set. Can you talk through what that is? When we did bar.x equals t, that made, we had whatever bar.x in the write, bar in the write set.
Right.
And then we wrote the bar.y equals t, that it was just, we just added the undo set, we didn't add another element to the write set.
Yeah, that probably is incorrect. Yeah, we probably should add an entry to the write set for both writes to bar.
Okay.
Yeah. Although, yeah, once since it's doing it by, you probably should.
Well, I thought maybe it was because it's all changed.
It is at the object level granularity, and so once you know that. Yeah, in this case, the write set isn't so important, right? Because you're doing pessimistic detection anyway, and you have an undo log, right? So figuring out, in this case, exactly what's in the write set isn't that important. You need, of course, to potentially on a conflict, use the undo log. But to be completely correct, you're right. You should probably have another entry in here for the other write to bar. All right, so we commit, and now we can, let's get rid of. Okay, so we're at the point that x2 waits. We get to the commit. All right, now what happens is we can now release the stall on x2. Right? And then we get another read from the x2 transaction, and this of course now has the new timestamp. Okay, so then x2 gets to the commit point, and what do we do first? Validate the read set. Okay, so we validate the first read, and does it validate? No. Right, so you have to abort, and once you've aborted, you can re-execute and then get the right values for the bar object. Okay. Any questions on how this works? Yeah.
On the SCM operations side, I don't think this really makes that much of a difference, but do we atomically update the global timestamp and then use the old one to make the read set validation?
Yes.
Or do we do it the other way around?
Well, let's go back to what was said. Yes, you atomically increment the global timestamp, and then you use the old global timestamp to validate the reset.
So the
Yeah.
global timestamp's updated first.
Right. Yeah. Okay. Any other questions on that? All right, then to summarize, right, so we've talked about the various options for TM implementation. We can be optimistic. We can be optimistic or pessimistic in terms of contention. We can be lazy or eager in terms of data versioning. And that with the software TM systems, the compiler or typically compiler or the virtual memory system adds these barriers, these software transactional memory barriers or instrumentation code to call into the transactional memory system to do the bookkeeping, okay? And the basic data structures are the transaction descriptor per thread or per transaction, and transactional records per data that keeps track of the state of the data, whether it's locked or version number. So it turns out, of course, that these barriers add overhead, and a lot of the work that gets done inside the barriers is in fact redundant. And so if you can decompose the barriers into the individual components, right? In fact, you've got a logging of the object, opening it for write, and you'll see that a lot of the operations that are composed in the barriers are redundant and can be optimized away, and so you get lower overhead. Then the question is, sort of, once you're done with this kind of optimization, what kind of performance do you get, right? So this is some data from one of the papers that was published on McCarty, and it's looking at two data structures, hash map and tree map. And for hash map, I think it was sort of 80% gets and 20% puts, right? And so you look at the different bars, this is the overhead on a single processor, right? So you're trying to look at sort of how much overhead you get. And so 0% would be the non-thread safe code. The blue bar represents the overhead by using a single coarse grain lock synchronized over the whole method. And the kind of reddish bar, purple reddish bar, is what happens if you use a software transactional memory that does not have any compiler optimization, right? So then you get 70 to 80% overhead on a single processor. However, if you combine an STM with compiler optimizations, the overhead comes down dramatically, as shown by this pinkish bar or pinkish orange bar. And then the overhead is roughly 40% over no concurrency control and 30% over a single kind of coarse grain lock-based synchronization. Yeah.
These percentages is reference to the percentage of the total work that is being overhead, right?
It's how much extra time it takes to run your code with these overheads in, right? And so if you have no extra code, then that's the time that you just got by running your code without any support for transactional memory or any synchronization at all, right? So it's not thread safe. So your code's not thread safe. You can make it thread safe with a coarse grain lock. As we've seen, that's fairly easy. Just in Java, just put synchronize around the whole method, right?
Well, it seems that would be a lot faster than the
Faster in what sense?
as in it's only 10%.
Yeah, it is faster, but remember, this is on a single processor. It won't scale. We saw that earlier, right? Didn't scale, right? So now, if you want something that's scalable, then maybe you have to go to fine-grained locking, which is actually not shown here, right? Or you go to transactions, and on a single processor, your overhead is 30 to 40%, but you really should compare it to the overhead of synchronization, since after all, if you don't put anything in your code, then it's not thread safe, and so you couldn't run it correctly in parallel mode, right? And now with transactional memory and compiler optimization, you get something that's both scalable with reasonable overheads. Okay. So just to refresh your memory, let's suppose that we have an atomic region and we are assigning 42 to the object field of F1 field of the object. what steps are required to implement the atomic region, assuming that there's some way of getting a transaction descriptor, and we're going to do things at the granularity of an object. What are the operations we need to perform? Once we have the transaction descriptor, what should we do? Oh, yeah, it's optimistic read, pessimistic write, eager versioning, just like the one example that we just described. We want to implement this atomic region. What steps do we need to take? Yeah.
Check if it's unlocked.
Right?
Like to validate and then you get the lock in your write set, add it to the undo log, and then write the data.
Okay, good. Right. So open for write is kind of your check, and you're going to log it, and then you're actually going to do the write since it's eager. Good. All right. So, here's some more data about the performance of STM, but here this STM is unoptimized, right? So it's not as optimized as the McCarty example with the compiler optimizations I just showed you. But the problem is that you've got this overhead in terms of performance, in this case it's 2 to 8 times per thread due to the software transactional memory barriers. And if we decompose the time, we see in these two examples, vacation is this 3-tier server example, k-means is just k-means clustering. And you see that a lot of the time, the white and the black portions of the stack bar chart are due to the STM write, which is black, and the STM read, which is right. So the STM barriers add a lot of overhead, and sort of committing also adds a bunch of overhead, right? And so the question is sort of how can we remove those overheads by judiciously using hardware? Well, we could try and attack the need to have barriers at all, right? And so if you have a hardware mechanism for doing transactional memory, then you don't need explicit barriers, right? You don't need to tell the transactional memory system, hey, I'm doing a read, or hey, I'm doing a write. Why don't you go take the necessary actions to implement the transactional memory? All I need to do is just do loads and stores and let the hardware transactional memory system do the correct thing. And so, as you might imagine, the way that we are going to implement this in hardware is we're going to ride on top or exploit the fact that we already have a coherent shared memory system, right? And we already have caches. And so we can do the data versioning in the caches, and we can do the conflict detection by riding on top of coherency. Okay, so we already have the mechanisms for implementing transactional memory inside a modern processor anyway. So we use the caches to do the write buffer or the undo log, and the conflict detection can be done by enhancing the coherency protocol. Okay, so the one component that you also need in order to take a checkpoint so that you can come back and abort is you need to checkpoint the register state, right? So you've got a context associated with the register contents of the processor, and you need to hold those values around so that when you abort, you can come back and get to the same state. So you need to checkpoint those away somehow, and a lot of processors allow you to do that. All right, so let's look at a hardware transactional memory design. So what we're going to do is we are going to enhance our metadata on the cache line, right? So we're going to add, for each cache line, we've got our messy state bits, right? Our coherence bits that we've already discussed, and we're going to add 2 other bits, an R bit and a W bit, right? What do these represent? The read and write. state, right? So if the R bit is set, says, hey, this cache line is part of my read state. If the W bit says this cache line is part of my write state. Okay? So then now you can think about how you do the conflict detection, right? So if you see a shared request to a line that is has the W bit set, you know that is in fact a conflict, a read-write conflict, right? So that you've already written this line, and some other processor wants to read it, and so there's a potential conflict there. If you see a exclusive request to a bit that's to a cache line that has the R bit set, then you know that we have a write-read conflict, right? You've already read the particular cache line, and some other processor wants to read it. Okay, so that again, of course, is a conflict. Another example would be, hey, the W bit's set, and you see an exclusive request that says, hey, there's a write-write conflict. I've already written this cache line, and this is other processor that also wants to write it, and we're currently both inside a transaction, and so something has to be done to make sure that we deal with that conflict. All right, so with that in mind, let's look at an example. So we have in our CPU the registers, and the red state, kind of is indicating the extra state that we need to implement transactional memory. So we've got a register checkpoint that we need to take, and then we have some extra state associated with, abort handlers. Where exactly do you go in the program to deal with aborts if there's any, software cleanup that needs to be done? And then the key elements that we've added are read R and W bits, right, which indicate our transactional memory state. Okay, so R says it's part of the read set, and W says it's part of the write set. So, given an example now, this is a very simple transaction. Loads A and B and stores 5 to C, and then we commit. All right, so first thing that happens is we load A, the cache line becomes valid. Let's assume, for the sake of simplicity, the cache line size is a single word. And we also have to indicate that it's part of the reset, right? So we need to set the R bit. Similarly for B, we set the R bit for the B address. And then for C, we probably want to put a 5 in here just to be correct, right? So this needs to be part of the write set, okay? So now that we get to the commit point, right, we need to, let's assume that we did not see, we'll get to the commit point, and assuming that there have been no other conflicts, what should we do? So, in particular, is this value that we wrote to C, how do we indicate to the rest of the system that, in fact, this is data that is actually committed state? So at the moment, it's inside our cache. We've indicated it's part of our write set, but the rest of the other transactions and threads don't actually know about it, right? Because remember, the property of transactions that we want is isolation, right? That each of these transactions is isolated from each other, and the way that we get that is that each of these transactions are operating on their individual caches, okay? So now we get to the commit point, and we need to publicize the fact that we have written to the address C. Okay? So how do we do that? Yeah. You need to upgrade it to the exclusive state. That's exactly what has to happen. So we need to get an upgrade, and so now we indicate that C is now in the dirty state, so or exclusive state, and we send that out to all the other processors. And let's suppose that some other processor was doing commits of a transaction with rights to A and D before this transaction committed. What would happen, right? Well, if we saw an upgrade to A, right, then we would say what? Conflict, right? Right? Because A is in our cache and it's part of our read set, right? And so note, maybe you read A before the transaction started, then it could be in the cache but not have the read R bit set, right? So, just the fact that A is in the cache doesn't mean that there's going to be a conflict. But if there is, in fact, the R bit set, then it says, hey, not only is it in the cache, but I read it during the transaction. Okay? And so now this would be a conflict. And this other case is where I see an upgrade for D. What happens as far as this transaction is concerned? Nothing, right? D is not in the cache. There's no no match with the entries in our cache, and so there can be no conflict. Okay? So let's assume then that we, going back to the commit, right? So we validate by requesting the write set lines. We commit. So as kind of described so far, what do we? How would you describe the policies in this hardware system? Think about it. Well, in terms of the data versioning policy and the conflict detection policy. It's eager, right? Because is it eager?
Every time you're trying to write a read,
But when do the upgrades actually take place?
at the end. Sounds optimistic to me.
And then in terms of the data versioning, it's also lazy. So it's lazy optimistic. Yeah. That's the way to think about it. Yeah.
Basically, we're using the cache as like the logs and stuff.
It's the write buffer. It's the write buffer. So it's buffering the writes, and then at the end of when you get to the commit point, you say, okay, here are all the things I wrote. Now I'm going to publish them to the world, and anybody else who happened to have. So it's exactly the case that we described, right? Which is you get to the commit point, you have a bunch of things in your write set, you're going to compare them to everybody's read set, and how are you going to do that? By sending out these upgrades. Yeah.
Just trying to relate this with the existing cache coherence, right? Like now when we try to store C, in general, what we would do is we would go to an exclusive state if it was not present in any other cache.
Right.
Like here we use the exclusive state as a way to indicate that, hey, I'm upgrading and limiting.
Right.
So in this particular pragma, do we think about whenever we read something, we go to the modified state first, and then I'm just trying to think of it from a protocol transition perspective.
So, as far as the state of the cache line, remember, it's all, it's isolated, right? So you don't really participate in coherence until you get to the commit point.
Okay.
Right?
That makes sense.
Yeah.
For the cache lines that are in the read set, I know for the write set we have to issue a read exclusive. What do we have to do for the read set? We just issue like a read non-exclusive, or
Yeah, you just do a read, right? Let's assume that you go get it from memory. It's shared, right? Or you do a read, you get it from memory, or you get it from whoever had it in its modified state last, right? Okay, so we've determined that this is in fact lazy optimistic, right? All right, so we can do the review. Let's do one more example just to kind of, really, this is in fact an explicit lazy optimistic scheme in which you're not, the way that you do coherence is with the transactional memory system, okay? So the idea here is that when you get to a commit point, you take all the state that you have and you update everybody else, okay? Which is classic, lazy optimistic, but there are no other states, right? Because all that ever happens is transactions execute, they get to the commit point, and then they send out all the state that they've modified and update everybody else, okay? So that's what's happening here. We've got a bunch of processes, 3, and then each of them is executing transactions that do reads and writes to different variables. The assumptions are there's one commit per execution step across all processes. And the reason you want that for simplicity is, hey, there's only one, it's kind of like a bus-based scheme that only one transaction is committing at a time and it's updating everybody else. Okay, and when one transaction causes another transaction to abort and re-execute, you can assume that the commit of one transaction can overlap with the begin of another transaction. Okay? So with that in mind, then, the idea is given these processes, 3 processes, and these 4 transactions, why don't you lay out the, fill out the table as shown here, right? So what actions, what's the read set on P1, the write set on P1, and the actions and read and write sets on the other processes, right? And so it's partially filled in here, right? So we started executing transaction 1 on processor 1, and at the point at which we do this write of C, A is in the read set, and A is in the write set, and C is in the write set for processor 1. A is in the read set of processor 2, is in the, and so on. Okay, so now we're at the point which, let's see. Which C commits. Okay, so what do we do in order to validate the Sorry, processor 1. C, yeah, it's commit. C is the commit. So yeah, transaction 1 commits on processor 1. What do we need to do? Yeah?
Nothing in its read set is in someone else's write set.
So what's the rule for lazy optimistic?
Or the other one.
What's the rule for lazy optimistic? We just talked about it. We saw it last lecture and a couple times today. Someone tell me.
You match what the right said to other people think said.
Exactly. Okay, so what's the right set of this committing transaction? Okay. What is the right set of read set of the other transactions? Doesn't have any. So it looks like we're okay. I should have gone back to this last case. How about this case? Transaction 2's committing.
Transaction 4 has to be started.
Yes, transaction 4 has to restart because the read set of transaction 4 contains E, right? So, you know, the rule says, hey, when transaction 2 commits, we can overlap that with the beginning of transaction 4, which had to abort and restart. Okay? So anyway, you can go and look at the details, but in general, you should be able to solve problems something like this, right? Given a sequence of transactions and, you know, you can figure out, and some rules to follow, you can figure out what happens. Yeah?
In terms of how this is actually like, can we assume it's all exactly the same time, or we just look at, like, the other processor just taking the bus and then they see?
Yeah, just assume that at the time that the commit happens, right, it's globally known what was in the write state of the committing transaction or processor.
Is it serialized? Can you have two bus transactions so simultaneously in that?
No. I mean, we could imagine systems that are not buses in which that happens, and in which case, you know, the problem would be a lot more difficult. But with a bus, the nice thing about it is only one transaction can be on it at any one time, and that simplifies matters, right? Because you know, we always like to serialize things because serialization means it's easier to think about and easier to reason about, and buses give you that serialization point. Yeah.
From an instruction set perspective, so we just put atomic and then brackets around, let's say, for getting the begin T1 and commit.
Yeah.
So is that an explicit instruction in hardware from an IC standpoint?
Yes, it would be. It would be. Yeah.
I'm just at this stage now, like transaction P1 is committing, and it has a C in the right set.
Right.
And transaction P3 also has a C in its right set. So it should abort it.
Should it?
No, data reset.
The reset matters.
It's like overriding.
It's overriding. Yeah.
That doesn't matter.
Yeah. The question is who gets there first, right? But but from the point of view of the consistency of the data, it doesn't matter. It never read it. It just overwrote it. So you'll still get the right result. Yeah.
Oh, when you said like bus serializes, if you just duplicate the bus, is that kind of how you get parallels of the bus? Or space of the bus?
You could have multiple buses, right? And then if you have multiple buses, then you've lost your serialization benefit, right? And now you've got to think about different schemes.
To figure out where you actually
Right. Yeah. I mean, all of these things are necessary if you want scalable performance, and buses don't scale, right? We only think about buses because they're easier to talk about in classes like this where, if you go back in time, yes, the earliest multi-port processors were in fact bus-based, right? Because that was the simplest to implement and building hardware was very expensive. But today, nobody builds anything with a bus, right? It just doesn't perform well. Yeah.
At the end of this example, like on this very slide, if we just go to the end of the table, we see that when we're committing T4, T3 restarts, I believe.
Where?
If you just go one more next slide. So in this case, I just want to clarify that the reason for this is because there is a conflict between is it the conflict between E, which is it's in the read set for T4, but
so the write set for T4 is
there's no
B and C.
But there's no conflict between the write set of T4 and the read set of T3.
Begin of T. Hold on. You said it was restarting, but I don't see the restart.
For CT3, is that another?
No, that's committing.
So
is there a stall between WE6 and CT3?
yeah,
That's
Stall which we're talking
Sorry, yeah, not restart.
So can you only commit one at a time? Is that why we're stalling?
Yeah. That was the rule that you can only commit one. Yeah.
oh, I see.
Yeah.
WC4 and WE5 basically in P2. Like based on the code that we have.
Yeah, it's possible. Yeah. I won't guarantee there's no bugs in there. Yeah. Probably should fix that. So, somebody's paying attention. Any other questions? All right. Gosh. All right, so, hardware transactional memory support has been implemented in Intel architectures. For various reasons, it didn't work out so well. The software to use it wasn't developed as well as one would hope, and it was not all that capable in the sense that transactions could abort for almost any reason whatsoever. And a lot of the times you had more aborts than necessary. But what finally kind of put the nail in the coffin of the transactional memory support was it opened up security holes that people exploited. And so, there's still in the Intel, roadmap, there is the plan to put in transactional memory, but we haven't seen any implementations yet. So if you look at the Intel ISA manual, then there are the definitions of a bunch of instructions to support transactional memory, but the latest implementations don't have them in. Just to recap then, transactional memory implementation, you can do software or hardware. You have the ability to make these trade-offs between the different points in the design space. And that if you really want to reduce the overheads of software, then hardware is kind of a key requirement. And once you kind of understand cache coherence, it's a minor delta to understanding how you would implement a transactional memory system. Yeah.
It's just surprising that towards the end of the lecture you just told that maybe Intel is not, currently it's not very widespread, is it, the use of transactional memory? And so this is with x86, I assume, because you spoke about Intel.
Yeah.
But does RISC-V even think about supporting something like this?
Well, RISC-V is is flexible, and
so the extensions means that I could add something.
you could add something to it if you wanted. IBM has also implemented processes that, and so has Sun before they got acquired by Oracle. So lots of people have experimented with it. In terms of sort of commercial uses of it, there's been more software, but software where you kind of localize the transactional memory used to places that would be very difficult to implement with locking, right? So there's certain database system implementations that kind of use, at the core of the database management system, use transactional memory ideas in order to implement parts of the system. Yeah.
I had a follow-up to that. So I think one thing I realized in the previous slide was one of the major problems was if something goes out of the cache, for example, then you basically abort and restart. Right. Like having companies thought about like having a separate cache or somehow prioritizing.
Well, you never want to specialize, because if you specialize, then you don't get to use those resources for other for programs that are not using transactional memory. So you'd like to reuse the same resources.
What about some sort of a priority order? So I understand we use B specifically.
There's lots of literature on every kinds of, transactional memory has been an area that has generated a huge amount of it, you go back 10 years or so, and there's just a lot of work in this area, and I can point you to it, and it's probably, if you just type in transactional memory to Google, you'll see an unlimited number of ideas and papers. So yeah.
So I guess my takeaway is it seems that theory transactional memory works better in fine-grained locking and less fine-grained locking, but in practice, commercially, it's not really used that much.
It's not used that much because, it's not used that much because you have to have this transactional memory system implemented in software, right? And you need, in order to really get good performance, you need compiler support, right? And and then you've got something that is not completely general, right? In the sense that now you now need to clone your code in order to make it work with the transactional memory system, and so that makes it the whole system a little less robust. And so the right way to think about the ways in which transactional memory has really been used is people come up with data structures that are optimized for working with transactional memory. And then they have part of their system that is being implemented with transactional memory, but they're not using transactional memory over the whole of their parallel system. They just kind of localize the components of it.
And with that localized component, you run with the cache coherence protocol?
It's usually, most of the commercial systems that use transactional memory use software-based schemes. Almost nobody uses the hardware because the hardware is broken. Yeah.
Is there any time in the future where it's actually going to work? Like in the hardware?
That's a good question. It's an open question. Yeah. All right. I think we don't have much time to talk about heterogeneous parallelism, but let me kind of get going a little. So far we kind of talked about using processors and GPUs and sort of SIMD execution to exploit parallelism. And the focus has been on sort of general purpose computation and writing parallel programs that are fairly general. And however, it turns out that if you want to get much better efficiency in terms of the use of your hardware, you might want something which is much more specialized, right? And so what we want to talk about today, or in the couple of minutes, kind of just introduce the idea of sort of what can you do to specialize your CPU to make it tremendously more efficient, right? So we've talked so far about, given the current set of resources that you might have in a modern CPU and modern GPU, how do you use those most effectively? But you can go further and say, what if I've got something that I want to, some algorithm that I want to run very efficiently? How can I make that work much more energy efficiently? Okay? So, you kind of look at across most real-world applications. They've got complex workload characteristics. Some of them have parallelism that you can exploit using multiple threads. Some of them have SIMD parallelism that you can exploit by using vector and SIMD execution. If you look at the memory accesses, which of course are a key component to the performance of your application, some parts of those, some of the memory accesses that are being made are predictable. And if they're predictable, then of course you can prefetch those accesses. If they're not predictable, then maybe they cache well, right? So hopefully you can get one or potentially both of these characteristics, okay? And so the question then is sort of, if you want to be able to exploit the wide variety of characteristics of the application space, then maybe you want to specialize your components to exploit the particular characteristics of your application, right? And so that's the idea of heterogeneity. And it turns out that all modern processors are in fact heterogeneous, right? So take the Skylake processor, that's the Intel Core i7 core architecture in your myth machines, right? They are in fact heterogeneous, right? So, the focus of our programming has been on the CPU cores, right? And their associated caches. But of course, they've also got an integrated GPU and graphics and media unit, which takes a significant amount of the area of the chip. And they've also got some other specialized components, right? So the point here is that this heterogeneity means that you can get greater efficiency in the use of the resources of the silicon and in terms of the use of energy. But of course, it creates a more difficult programming paradigm, right? We've already seen that you need multiple threads for the CPU cores. You need some sort of data parallel programming model like CUDA for the GPU, and you might need a different programming model for the media components, right? And so next time we want to talk a little bit more about the types of heterogeneity that you might see in the modern computing landscape, and talk about how you address some of these programming aspects, especially for applications such as the ones that you're doing in your programming assignment. Machine learning applications. So we'll continue that next week.